test, and the test is about torsion. That is lab number 5. And I'm going to start here by showing you the meaning of torsion. So before I do so, I would like to remind you of what we covered so far. So in lab number 1, we simply covered the hardness of material. In lab number 2, we covered the resistance of the material under impact load. In lab number 3, we tested steel and cast iron under the effect of tension forces. And in lab number 4, we tested same two materials under compression force. Now here is a slide to show you the three things on the same picture, I would say. So the top is our specimen in tension, where tension is a force that tends to elongate the member, and it is parallel to the axis of the specimen, and it causes something called normal stress. So the stress is perpendicular to the surface, to the cross section. The stress is a normal stress. It's a perpendicular to the cross section. Compression is exactly the same thing with difference by reversing the force direction. So you can see compression is a force tends to shorten our member. It causes also an axial stress, which is perpendicular to the cross section of our specimen. So this is something we already cover, and I need to remind you whether tension or compression, we apply the force, and the force is measured in kilonewton units. For today's class, we will look at the bottom left picture in yellow, which is a torsion. And you see what torsion is from this picture. It looks like we're applying a twist. We're trying to twist the specimen. And really, I want to emphasize a couple of things. Number one, in this case, there will be two stresses, two kind of stresses. And one stress is a shear stress, and shear is not normal. Normal stress, it's perpendicular to the cross section, while shear is in the same plane of the cross section. So the stress is parallel to the cross section, not perpendicular. Also, along the longitudinal fibers of the specimen, you will also see some tension. Uh, Probably I can show you my pointer to make it clear. So what I'm saying here is that when you apply compression, this is the direction of the stress. It is perpendicular to the cross section. Same as tension, this will be the direction of the stress. Also perpendicular to the cross section. We call those ones normal stress, normal stress. How about the torsion? Please watch this. So as we apply this twist moment on the cross section, so there will be stresses going this way. So in the same plane as the cross section. So this is called shear stress. And also on these fibers here, we will get some tension stresses. So I need to also to remind you that the torque or the twisting moment, it is a moment which is the units will be force multiplied by lever arm. So the twisting moment or the torque is a force multiplied by a lever arm, and the units will be Newton meters or Newton millimeter or kilonewton meter. All these combinations are torque units. Okay. Now, before we start our actual test, I would like to just briefly, without going into details, I found out last class that some students they are able to identify and look at the structure and are able to identify members which has torsion, and some others cannot. I will just try quickly to run the exercise. I want to, try as best as I can to show you when we talk about torsion, where torsion exists in our structures. Okay, so I'm going to start here with the top right picture. The top right picture. What you see on the top right picture here is that this is I would say maybe a house or maybe a wood building. It's not a house; it's a wood building, and this wood building is still framed. not covered yet, where you can see trusses. So those are trusses, roof trusses. And typically for wood structures, we typically have an eave straw, something that extends outside the building by roughly about 2 feet. And this is the way you frame it. We have those members here, those wood elements here. We extend them outside to support the eave straw. And then we have a back span, and this back span is hold back and anchor to here at the back truss. Okay. So in this case, there is no torsion because simply here is one member. So this one member here, and this member will be under bending moment. So under the gravity load of the eave straw, simply this member will be under bending. Same thing here. Look at the bottom right picture. The bottom right picture, which is a canopy. Typically, we build canopies at the entrance of the buildings. And this canopy here, the way it's being supported is using those cables or wires. So we hold back the canopy by wires, which the wires are anchored back to the structure. Okay. Now I want you to look now on the bottom left corner image. So what you see on the bottom left corner image is a shed or canopy, and simply we have some columns. So we have a column here and a column over there and also a column. So a series of columns, and in between the columns we have this longitudinal member. We have a beam connecting those columns. And I'm asking you, you can see there is here a beam which is framed outside from this beam. Please try to understand that when we have a gravity load like a snow on top of this canopy, what happened is this beam is wanting to go down and it's connected to this beam, so it will cause torsion because you can see the moment is simply around the axis of the beam. So that's why it will cause torsion. And I will say same thing here. The top right, top left picture, the top left picture, we also have a canopy, and the canopy, there is no cables, there is no column. So the only way for this canopy to stay in place, it will cause torsion. So we have a beam here, and you can see if I apply gravity load here, so it will simply cause this kind of bending moment around the axis of the beam, a twisting moment. Okay, here is another few pictures. Look at this pretty structure on the top left. I'm asking you now, since you know a little bit about torsion, I'm asking you, the top left picture, do you think the beam in between the column will have some torsion? I'm referring to, so this is a column here, so this one column here, another column over there, and in between there is a beam. I'm asking you, do you think this beam would have a torsion?
Yep.
Yes, it has. Look at this place. Look at the canopy. So the canopy under gravity load will try to go down, and it will cause a twist around this beam here. So this beam will be in torsion. Okay, now next is look at the top right picture. Do you think there are some framing which we don't see, but there is for sure there is a beam here to the building. I'm asking you, this beam here, do you think it will have torsion?
Nope.
No, because of those cables. I look at those cables. So those cables are holding the canopy up, and your beam won't have any torsion. Now let's do the last exercise. Not the last. We still have two. The bottom right picture. Do you think this beam close to the building is not very clear from here, but there is a beam over there? I'm asking you, do you think this beam would have any torsion?
Nope.
Thank you, sir. Because why? Because those columns, so those columns are holding the canopy up, and that's why this beam doesn't have any torsion. The last one is super hard. I know that probably it's very hard for you guys to figure it out, but let's see. On this picture here, do you think uh, any element would have any torsion? And
Nope.
just please think, please think. I know that this is not easy. Even for me, it took me some time until I figured it out.
No, no torsion.
I think there is no torsion, and I know if you don't follow it, here is my understanding. Although some of the framing is visible and some of them they are not visible, but this is my feeling. So you can see here we have those joists here, extending between those outriggers, like the blue ones are outriggers, and so the load will go from the joist to the outrigger in blue, and then this blue thing simply it goes, and I bet you that there is some columns here. So there is a column here, and there is a column here, and there is a column here. Okay, so those outriggers in blue, what they do is they simply cause a bending on the column, not torsion on the beam. Look at the framing and you will know. If I reverse those like reverse those joist, like my joist will go this way, for example, like this way, perpendicular to the building, I would say there must be here something in between the columns, like a beam, and it will do the same thing as here. You know what? If you don't follow the discussion, I would not stress you. I know this requires probably some experience, and I can understand that there are most of the framing in these pictures are hidden inside the structure. So, you know what? Let's take it easy. Let's move on to our next discussion, which is the test. I always wanted to connect you like about the test to the real structure. Where can we see this in a real structure? So let's get started with the test. So our test today is called ASTM A938, and it's a standard test method for torsion testing of wires. Uh, in this test, what we will try to do is we will develop a torque angular deformation curve for steel and cast iron. You guys remember in the last two labs, what we were trying to do is we were able to establish a relationship between stress and strain in tension and compression. We will try to do the same thing. We will see if I apply this much torque, what happens to my specimen. There will be some deformation as you have seen on the first page. Okay, so we'll try to establish this relationship. Number two, we will confirm the published values of shear modulus. If you guys remember, in the last two labs, we looked at something called the modulus of elasticity, where the modulus of elasticity represents the rigidity of the specimen in tension and in compression. In tension and in compression, we have a very similar number as a material property, but not really in tension or compression, rather than in shear. So if we apply a stress in shear, also the material will kind of respond to us based on how rigid the material in shear. Huh? So it's kind of very similar concept to the modulus of elasticity, which is normal stress, called shear modulus. We will know about this a little bit later on. And then finally, our last task in this class is to be able to observe the failure modes. And we've done this already in tension and compression. We looked at when we apply tension, how my specimen would fail. Like I look at necking, if you remember this word, necking for tension and shear failure in compression. And we always try to compare between the behavior of cast iron against steel, because one of them is brittle and the other one is ductile. Okay, let's get started. So here is our test picture and the specimen. So we have a machine at SATE, and this machine basically it has two heads, the ones you see in green. So this is number one. So this is head number one, and this is head number two. And in between here is our test specimen. And I need to be clear before we start. This specimen, the one that you will see shortly in a video, it is not a cast iron or even steel. Until now, we bought this machine a couple of years ago, and until now, with even the help of the company, we're not able to get a good results from the steel or from the cast iron. So to show our students some demo, we replace the steel or the cast iron by a plastic bar. So what you see here is just a plastic bar between the two rotating heads. So as I said, we have two heads. One is fixed, It doesn't rotate on the left. And then on the right here, we have a rotating head. Okay, and we simply clamp the specimen in between. And let's see what happens during the test. So I just want to stop here and see your observation. So can I ask you, what is your observation so far from this test? What do you observe so far?
It doesn't really look like anything's changed.
Okay, so that's why I ask you. So look at the far right side. So on the far right side where my mouse, look at my mouse here. So I'm asking everyone to look at this. So there is here, there is a scale here, and this scale tells you the angle of twist. So as we apply a torque on this, remember this head is moving and the left head is not moving. So we're trying to twist our specimen. So I will run the test one more time, and please all of you try to look at the far right side of the video. Okay, so I wanna mention something before we continue and watching the rest of the video. A couple of things. Do you guys noticed what happened on the right side?
Well, it made a couple total revolutions.
Exactly, sir. And you can see that clearly from the right side when you look at the scale. It goes back to zero right now. And the other thing is, before we start the test, we draw a straight line parallel to the axis of the rod, and you can see it is coming here. So we just try to mark what happened to the deformation on along the center line of my specimen here. Okay. So I think we'll keep watching. We'll keep watching. Okay, so this video, actually, when I was in the lab, it took like so many rotations. I will show you how many rotations later on did it take to break the specimen. And here is our, final. So this is when the specimen, but the video were too long. That it was too long, and in terms of size, it was like few gigabytes. So that's why I didn't want to show you the entire video, because simply the machine will keep rotating, rotating, rotating until the specimen breaks. But you can imagine, look at how many cycles did it go through. You can count them with the black line, like 1, 2, 3, 4, 5, 6, 7, 8, and probably there is one more to the right. So about 8 or 9 cycles until the specimen breaks. Okay, so before we proceed, I want you to look at those pictures and try to identify the deformation to the specimen as we apply torque. So look at those grid lines. We have a straight line. That's where we originally start. And then by applying torque, all those will be deformed. Now we talk about the failure mode. So we always see in our class here, we put mild steel against cast iron and we see what happens to them. Part of your lab, you will need to sketch. And I need to be clear, when if the lab says sketch, it means we ask you to draw a sketch, because some of you already provided the lab, I think the last lab tension, and never provided a sketch. So please do, huh? So all you have to do is just look at this picture and try it with a hand sketch to draw what was the failure mode. So for mild steel, what happened here? The failure was due to shear. I'm going to show you my pointer. So here is how it fails. So there was a shear forces due to the torsion. So we apply a twist here. So this will cause shear forces, and the failure is due to the shear forces. How about the cast iron? The cast iron, we know that as we apply the torsion, there will be two stresses, a shear and also a tension. And probably I can go quickly to the first page here. Please look at this picture one more time. As we apply torque, there will be two stresses. Stress in the plane of the cross section, which is a shear stress, plus also plus tension in the longitudinal fibers of your specimen, along these fibers, okay, parallel to the axis of the specimen. The cast iron will fail in tension, and it will look like a spiral, and it's a brittle failure. While mild steel, we know that it's a ductile material which will fail after it heals. Now here is some equation, some math. I know that you guys are working with Corwin, correct? Are you?
Yep.
So I checked with Corwin on his progress on the lecture, and he mentioned that he did not start the torsion yet. Did he?
No.
Not yet. And that's why probably this will be a little bit, I'm not saying it's impossible, but I can say it could be a little bit hard for you, because really the lab, I don't know which one should come first. The lab comes before the lecture, or lecture comes before the lab. At the end of the day, if you hear the same thing twice, I would say you will feel much better about it. So I know that some of you, or sorry, all of you are hearing the word torsion for the first time, and it become even more difficult when we show you some equations. Okay, but you know what, I'm not trying to scare you. I will try my best to simplify things, but here is my point. If you don't get the discussion 100%, let's say I got it 70%, I would say still okay, because simply very soon, probably next class, like Corwin will discuss with you this torsion equations in details. I'll try as much as I can to make it simple. Okay, so let's do it. Okay, now we talk here about, and I think I had the same, almost same slide on tension and compression, where I showed you the meaning of stress and strain and modulus of elasticity. We have exactly the same thing here. I'm going to show you the math that controls the process. Now, this one here, this graph here is simply the cross section. So remember, we're applying a torsion or a rounded bar. round the bar like circular cross section. So on this cross section here, when I apply torsion, remember the torsion goes this way, huh? The torsion, it's a twist moment. And where is the axe of the bar? It is simply perpendicular to my screen. The axe of the bar is perpendicular to the screen. So when I apply torsion, capital T, it's a twisting moment. What happened here is there will be stresses on the cross section, and those stresses are not normal stresses, those are shear stresses. We call them tau. So we use here tau, and it's not T, huh? We use a Greek letter called tau. So this tau here, it varies. At the center line, at the center of your cross section, there is no stress. So the tau is equal to 0. As you go away from the center line until you go to the surface of the specimen, the shear stress will be maximum. That's why we talk here about tau maximum. So this number here is your maximum shear stress, and it's on the surface, okay? So all the points on the surface here, all those points, they have a maximum shear stress. How much? Not very difficult. It is very simple. It is the T multiplied by C divided by J. And I will show you what every element means. T is the applied torque or twisting moment. And you guys know that torque is a force multiplied by lever arm, which means, as I said before, it is measured in Newton millimeter or Newton meter or kilonewton millimeter. All those combinations are torque units. The C is the bar radius, which is simply from the center to the extreme. So that's called C, the radius. We typically use R, little r for radius, but in your book it says C. So we will just follow the book. So C, and even Corwin will use the same symbol. We'll use little c to represent the radius. And the total, so the total diameter is called D uppercase, and that's the bar diameter, which is simply twice the radius. Finally, the one that probably it will cause you a little bit of pain, which is the J. What is J? J is something called polar moment of inertia. Please be patient, Please be patient. J is the polar moment of inertia, and it is simply estimated in millimeter to the power 4. Now, what is J? You guys probably by now understand that if I give you any section, for example, a square, a rectangle, a trapezoidal, a circle, any geometry. For this geometry, it has some properties. Properties, for example, what is the area? Where is the centroid? Where is the center of the gravity? What is so those are called geometrical properties. They have nothing to do with the material. It is the same for if this section is from wood or concrete or steel. It has to do with the shape and the size of the member. So one of those properties on a very high level, I'm not going into details, just J is something called polar moment of inertia. And probably you'll study also in your class something called I. And I is something called moment of inertia, okay? Or something called second moment of area. In different literature, they call the same thing different names. So I, it's called moment of inertia. And in some other literature, they call it second moment of area. And J is the same thing, but it's around the axis of the specimen, called polar moment of inertia. It is measured in millimeter to the power 4. As I said, on a very high level, it is connected to the size and the shape of the cross section. So how can we estimate that the J? Is very simple. J for rounded bars or shafts is equal to, you know what? I'm trying since yesterday. I don't know why. Every time I change the symbol to the right one, it goes back and say a question mark. Looks like it's missing the font. But please change or do it manually. Understand that this is pi. So it's pi multiplied by the diameter to the power 4 divided by 32, which means you can see it is function of the size of your specimen. And also, if you take a different cross-section shape, like a square or rectangle, you will see J will be different formula. So all I want you to know is J is function of the size and the shape. The size and the shape. For rounded bars, rounded solid bars, the J can be estimated using pi, which is 3.14, multiplied by d to the power 4 divided by 32. Okay, so now you know what does it mean stress. And that's how we estimate the stress. And remember, if I want to estimate the stress anywhere between the center and the outside, I need to replace this C here by the distance from the center to this point. Obviously, the maximum is at the very end, which is the surface. Now, next one is something called twist angle. Twist angle. And you guys have seen this in the video. When I apply your torque, the whole bar will twist by an angle. And here is my twist angle. We call it phi. So we use the letter phi or the symbol phi, which is another Greek letter, to represent the twist angle. And you can see when the specimen failed, the twist angle was almost about 8 multiplied by 360 degrees. So the bar rotated 8 times. So you know every cycle is 360 degrees. 360 degrees. So if we have 8 cycles, it means 8 multiplied by 360 degrees. So this angle is simply, this angle here is in proportional to few things. Number one is the torque, and it makes sense. If I apply more torque, for sure. If I apply more torque, I get more twist angle. Do you guys agree? If I increase my torque, the angle will increase. Yes or no? I'm asking you. When we increase the torque, do I get more twist angle?
Yeah.
Yes.
Okay, one more thing. How about if I increase the length of the specimen? What do you think? When I increase the length, do I get more torque angle, sorry, twist angle, or less? You need to think about this. You need to feel it. If I make my specimen very, very long, does it become more stiff or less stiff?
Less.
Less stiff, and that's why if the longer the specimen, you get also as a more twist angle, and that's why you can see T multiplied by L. Now let's look at the denominator, and the denominator looks like we have inverse proportion. It means when this J or G increases, it means we get less twist angle. So there is an inverse relationship. I'm asking you, if we have a bigger bar, okay, are we getting bigger twist angle or a smaller twist angle? Bigger bar, it means the diameter gets bigger, so the J gets bigger. Do we get, if we have a bigger bar, do we get more twist angle under the same twisting moment, or less?
Less.
Less, because my member becomes more stiff, and that's why when it becomes more stiff, then you get less angle. The last one is the discussion today, which is coming, the G here. So you know everything so far. You know what's T, which is the torque. You know the L, which is the length of our specimen. And then you know the G, which is the polar moment of inertia. Lastly, the G, which is our discussion next. This is called the shear modulus. The shear modulus, which is a number that simply shows you the resistance of one material for the shear stresses, same as the E in tension and compression. So the equivalent of the G in tension and compression is the E. In here, it is not E, it's called G, which is simply the shear modulus. And it has the same idea of the modulus of elasticity. When we apply a stress, we get a strain, and in between the stress and the strain, there is a relationship. And the G simply controls this relationship. Okay? Really, before I let this part and I go to the next slide, I want everyone to be clear. The J has no business with the material. J is not connected to the material. It is connected to the shape and the size of the specimen. How about the G? The G is connected to the material. So if you're testing a steel or maybe cast iron, this number will vary, will change. Okay? And obviously, if we have a more rigid material, for sure we get less twist angle. So the relationship is an inverse relationship. Hopefully, this equation makes sense for you. And as I said, If you don't follow 100%, please wait for Corwin in the next lecture. He will give you more details about the torsion stresses. Okay, just I want to mention something very important, very, very important. Okay, I want you to look at the units. Look at the units of the T. It is Newton millimeter. And the length is the length, it's in millimeter. So now we have Newton millimeter square. And if we divide by G, which we already said it's millimeter to the power 4, and then the G is simply same as the modulus of elasticity, which is Newton per millimeter square as well. It's a stress unit. Guess what? If you have time and put all of those here, you will get that the phi from this equation is radian. Radian. It means unitless. Remember, any angle, we can say my angle is 10 degrees or 100 degree or 100 degrees. That's in degree. And also we can express our angle in radian. Radian is unitless. So just to remind you, I know all of you know this one, but I want to remind you, and that's why I put it in red box here. When you have an angle in radian, so this is equal to the angle in degrees multiplied by pi divided by 180 degrees. So if you want to convert your angle from degrees to a radian, then in this case, you just take your angle in degrees, you multiply by pi divided by 180 degrees. Okay? And that's why, for example, if I have an angle of 180, so this will give you the pi. Okay? Now let's go to our slide here, which will simply, next we will look at the results right away. So this one here is our last slide, talking about the G, which we said G is the shear modulus. And by definition, the shear modulus is simply stress divided by the strain, which is, if you remember, E was the same thing. E was stress divided by the strain. The difference is the stress is not normal stress. This stress here is a shear stress, and the strain here is angular strain. Okay, that's the difference, huh? The difference here is that before the stress here was sigma, and epsilon, the strain was epsilon. Those are normal stresses and normal strain. How about the G? Those are shear stress and also angular strain, which is equal to tau. So guys, you know tau is a stress, and divided by gamma, which is an angular strain. Look at this. So where is gamma in this picture? So I showed you here one more time. Here is my specimen. I'm applying to torque or twisting moment. I get the twist angle here in like the phi, and the length of my specimen is L here, and then finally here is your gamma. So gamma is simply the twist, the angular strain. So if you want to do that, and you will see how do we estimate the G, we simply say we take any 2 points on the curve. So if you remember last time, we had to we developed the curve between the torque. So on this curve here, we have here T, which is the torque, and here we have our phi, which is the twist angle. So in order for us to find the G, as you will see in the next slide, we will simply have to pick 2 points inside the proportional limit, and we can estimate the slope of this line, and the slope of this line will be simply your G. Okay, the G. Okay, so let's go to the next slide, and I will show you in more details, because next slide it will show this even better. So this is what you will see on the lab. So on the lab, I provided you some data which was collected in SATE a year ago, I guess. I think a year ago in 2019, or more than a year ago. And so in the lab, we provide you with some graphs. So the first graph is between torque. So as we apply more torque here, we get more angles. And this graph is developed by the machine. Remember, the machine will simply measure the torque and will measure the angle and is able to plot for us this graph. So you can see the graph is very similar to what you've seen before. We start here with the linear relationship, then we have a curve, and then it goes to horizontal, which is kind of yield. Look at this part here. This part here is the yield, where you don't have to add any extra torque to get extra angle, extra twist angle. And then after the yield, it goes up a little bit and then it fails. So this is the behavior of my specimen. So there are some few facts here I want you to understand, which is very important for you in the lab. If you have been sleeping for the last 30 minutes, please, you need to wake up now. It's very important. What I'm going to say right now is going to save your life when you do the lab. Number one, what you will see is you will see in the lab data, there are some another graph, and this other graph still torque and then angle. So what this graph is simply a magnification or zoom to here. So you will see this graph number one on the lab data, and this is graph number two on the lab data. Okay. So why is that? Because simply when we estimate the G or the E, we have to be in the proportional limit. You guys agree? When we estimate the E, which is the modulus of elasticity, or the G, which is the modulus of shear, we have to be in the proportional limit. So we have to be on the line of a part of the curve. You guys agree or disagree?
Yep, that makes sense.
Okay, so the reality is we have here a curve, and look at the angle. The angle goes from zero, and look at the angle, please. It goes from zero and then 296. So it looks like we will have several cycles until the specimen breaks. Okay. The surprising thing is the proportional limit in torsion is very small. It's about 1 or 2 degrees. And that's why when we estimate our G, we need to be on the proportional limit, on the first part. And that's why we provide you with another zoom. So please, when you estimate your G, don't work on graph number one, and please work on graph number two. And as I said, all you have to do is we want to find, 2 points, any 2 points. For a better results, take the extremes. Take the first point, and the second point is your yield point, just before it start to curve. Okay, and all you have to do is watch this, please. So for every point, you have to find the torque, and you have to find the angle, and also for any point you need to find the torque and the angle. If you know 2 points, you know what to do. Look at this. You go here. Now you know the T2, you know the T1, and you know the L. And then you go and you know the angle phi 2 and the angle phi 1. So all you have to do is just find the J, which is not super science. The J is pi multiplied by d to the power 4 divided by 32. Here we go. Remember, this is pi. I apologize, I cannot fix it for unknown reason. So the J is pi multiplied by d to the power 4 divided by 32. So if you know the diameter, which is here. So guys, look at this. This is the diameter of our specimen, 18.4 millimeter. And I want to please be clear. So there are some other information on the graph. Please don't use. I already hide them on my slide. So don't use this part, and don't use this part. Until now, as I said, we bought the machine 2 years ago, and we asked the company to help us to change the setting to not to print these numbers, but it's still printing. Really, all you have to do is you have the diameter here, that's the D, the diameter, and here you have your ultimate T. So that's T maximum, torque maximum. That is all what you need to finish your assignment. And I did the same thing here. I hide this part, so this part is hidden, and also this part is hidden. So please don't use these numbers in your data. Okay. Now, as I said, look at this equation again. So you know the T2, you have 2 points, point 2 and point number 1. So you have the torque 2 and the torque 1. You have the angle 2 and the angle 1. So you're able to find the G, and that's part of your lab. Part of your lab is to find the G. Please understand that this phi 2 and phi 1 must be in radian. Look at this, please. To find the G, the phi 2 and phi 1 must be in radian because of the units. So which means here its angle in degrees. So you take the 0.7. If I zoom in here, for example, the phi 2 is 0.7, 0.7 degrees. And 0.7 degrees, you must multiply by, watch this, to turn your angle into radian, You must multiply the angle in degrees, multiply by pi, divided by 180 to find your angle in radian. Okay? Also, one thing you will see on the assignment is the assignment asking you, find for me the stress. So one of the requirements on the assignment is to simply find the G. Okay, we already went through how to find the G. Okay, the other requirement is we'll ask you to find the stress. Stress means tau, huh? We want to find the tau. Excuse me? Do you want to say something, sir? Do you guys have any comment? I hear someone is asking one question, I guess.
Sorry, I turned on my mic by accident.
Okay, sure, no problem. So guys, on the assignment also, or on the lab, is ask you to find the tau. Tau, it means stress, huh? We want to find the stress, which is super easy. This is how you find the stress, okay? So T multiplied by the radius, which is half of the diameter, divided by the J. And where is the J? It is simply this number here, huh? By D squared over 32. Now, the lab is asking you to find the tau for 2 points on the yields, and you can see here is the yield point, and you know the tau here, huh? It's about 17.5 Newton meter. And also it's asking you to find the tau at the failure. So how can I find the torque maximum? Anyone can tell me where I can find the ultimate torque? Anybody can look up my screen and tell me how much is my ultimate torque?
751 Newton meters.
Yes, sir. So look at this. By the way, so you know this is the ultimate torque here. So this point here is your ultimate torque, and you can go horizontal, and this will give you a 751, which is it's mentioned here. So all you have to do to find the stress is use 751 Newton meter multiplied by the C divided by the J. The only thing I would like to warn you is the units. Units, huh? Remember the stress. We typically get it in MBA, which is Newton per millimeter square. So make sure that everything is in Newton and millimeter to find the stress in the right units. Huh? You will have to do the same thing for steel and for cast iron. And I think one of the question is sketch. And you guys have seen the sketches here. Huh? So those are the sketches you want to draw a hand sketch. Now, the last thing before I let you go for a break. So I want to show you something that, and then let you go for a break, which is there are some tables. There are some tables on the lab. So I think here is your lab. So there are some tables on the lab. Please kind of cancel those guys, huh? So please cancel those guys. Those guys we used to ask our students when they attended normal lab to fill them themselves from the machine. So take the torque and take the angle themselves. Those are not required. Really, what you are required to do is the last page. You can see the last page. It's calculations where you have to find the G and you have to find the stress and finally sketch. So basically, your lab questions is the last page. Any questions so far? Any
So all you
questions?
want from us is just questions 1 to 4 on the
Excuse
last
me?
page. You
Exactly.
don't
Yeah.
want us to do anything with any of the tables.
No, 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 no. As I said, those tables are what you see on the graph. So simply, you can turn this graph into numerical. Huh? You can put here points, like every point on the graph is a torque, an angle. Huh? No need now. Just use the graph to find your information, your requirements like the G and the stress and so on. Any other question before we go for a 10 minutes break? Okay, so here is how we proceed, just like normal. Huh? I will let you go for 10 minutes break, and you guys know what to do after the break. You come back to your break-up groups. You work, download the data. Everything is available on the D2L. Make sure, please, before you forget, change this into pi. Huh? You can see here J is equal to question mark multiplied by pi. It's very surprising if I change this one to pi. I'll show you. Simply, it doesn't work. No matter how many times I do it, I change this one. to buy, I save it. Every time I show my presentation, it turns itself into question mark for unknown reasons. So please make sure you take the note. And I think this is even on the lab. So if you go somewhere on your lab, it will tell you here. I think it will tell you that the J is equal to pi multiplied by d to the power 4 of divided by 32. Even you don't do it, it's available on the lab. Okay, so after 10 minutes, please, you come back at roughly around 9:05. Go to your breakup group, and I will come sometime to check on your progress. Thank you so much.